So question 10a, the binding energy per nucleon iron is 8.46 mega eV per nucleons. Calculate the nuclide mass for iron. So means that we want to find the mass of the nucleus for the iron. So if we refer to the list of the equations given for topic 10, so we can see very obviously we can determine the mass of the nucleus by using equations 87. Okay, and the binding energy per nucleon, actually we can relate with the mass defect using equation 88, whereby binding energy is delta mc squared. But then in order to use these equations, our mass defect is in kilogram. When we multiply it with the speed of light, we will get our binding energy in joule. But then, class, if you recall what you learned in lectures, beside these equations, actually we know that according to the mass equivalence principle, one mass of 1 U will contribute energy of 931.5 mega electron volt. We might also relate the binding energy with the mass defect by multiply it with 931.5 mega electron volts, in which then we will get our binding energy in unit mega electron volt. Okay, so in order to solve these questions, to find for the mass nucleus, I'm going to determine the mass defect first using the binding energy per nucleon given. Okay, so we are going to have the binding energy per nucleons will be delta M multiplied 931.5 mega electron volts over the value of A nucleon number. So for iron, this value by this binding energy per nucleon is 8.46 mega electron volt per nucleon. So I can get the value of nucleon number by referring to the question. So 56 is the mass nucleon. So I can calculate the mass defect. So we are going to have mass defect equal to 8.46 multiplied the nucleon number 56 divided by 931.5. So I'm going to have the mass defect is around 0.508599 U. Okay, so once I get the mass defect, I'm going to use the equation 87 to find for the mass nucleus. So delta M, write down the equations, will be the numbers of proton multiplied mass for 1 proton plus numbers of neutron multiplied mass for 1 neutron minus the mass of the nucleus. So I put in all the value. The mass defect is 0.508599. So the numbers of proton you can read from the informations given. 26 is referred to the numbers of proton. The symbol for numbers of proton is Z. So the Z is 26. The mass of the proton, we can refer to the list of constant. Always refer to the list of constant in exam in order to get the mass of the proton, neutron, and electron. So if we refer to the mass of, if we refer to the list of the constant, the mass of the proton is 1.007277 U. And the mass of the neutron is 1.008665. Okay, so always refer to the list of the constant. So I put in the value. Mass of the proton is 1.007277 plus with numbers of neutron. How I'm going to get the numbers of neutron? So you might use equation 86. So we can get the numbers of neutron by taking the numbers of nucleon minus the numbers of proton. So I'm going to have 56 minus 26. I'm going to have 30. So the numbers of neutron is 30 multiplied mass of 1 neutron. So again, get the value from the list of constant is around 1.008665. Then minus the mass of the nucleus. Okay, so then we do our calculations. Then we will get the mass of the nucleus will be around 55.94 0.0553U. Okay, then we solve the question. So we move on to question B. The half-life of tritium is 12.33 years. If the initial activities of a tritium sample is 1.48 to the power of 10 BQ, calculate the numbers of nuclide after 10 years. So we want to find the numbers of nuclides, so I represent by N after 10 years. Okay, the question gives us the half-life of tritium in years. So the years we can change it to second. We can do all our calculation in SI unit. And then we are given the initial activities. I denote by A naught. So the initial activities is 1.48 to the power of 10 BQ. So BQ is the SI unit for activities, whereby BQ is decay per second. Okay, that's why we must change our half-life to seconds, so we will be consistent with the unit we use when we do calculations. So we want to find the numbers of nuclides. So if we refer to the equations that we have under radioactivities, so the numbers of nuclides we can relate with the decay constant and also the rate of decays using equation 89. So this rate of decays actually is referred to activities. Okay, so I want to find the numbers of nuclei after 10 years. So I have already identified the equations that I'm going to use. So I have dn over dt will equal to negative n. So the negative I no need to put in because I just want to determine the value only. This negative just telling us that the numbers of nuclides, the undecayed nuclide, is decreasing with time. Okay, so when we do calculations, we just ignore the negative. So dn over dt actually is the A. So I want to find the numbers of nuclei after 10 years. So the activities after 10 years will equal to decay constant multiplied the numbers of nuclei after 10 years. So in order to get the n, the numbers of nuclei after 10 years, I will take the activities after 10 years divide by the decay constant. So to solve this question, I have to determine the activities after 10 years and also the decay constant. So I need to get these two values first. I cannot put in the initial activities here because the numbers of nuclei that I want to calculate is after 10 years. So maybe very first we can determine the decay constant first. So using equation 92, whereby we relate with the half-life given. So we determine our decay constant. So the decay constant will be ln 2 over half-life. So I have ln 2 over the half-life is 12.33. So I put it in SI unit. So I have 1 year is 365 days, 1 day is 24 hours, 1 hour 60 minutes, 60 seconds. Alright, so I'll get my decay constant in per second. So it should around 1.78 to the power of negative 9 per second. So this is the decay constant for the tritium. And then I need to find the final activities after 10 years. I need to find the activities after 10 years. So since the activities unit is decay per second, so I have to make sure the time 10 years, I need to change it to second. So how we are going to find the activity after 10 years? We are going to relate with the initial activities. So I'm going to use equation 91. So I have A equal to A naught exponent negative decay constant multiplied time. So the initial activities is 1.48 to the power of 10 exponent to the power of decay constant is 1.78 to the power of -9, and the time is 10 years. So 10 years have to change it to seconds. So I multiplied 365, multiplied 24 hours, 60 minutes, 60 seconds. So I have to change it to second. Why? Because take note our decay constants is per second. So our time must be in second. So the unit must be consistent. The unit must be consistent. Then we will get our activities after 10 years. When we do our calculations, the activity should be 8.44 to the power of 9b cubed becquerel. Okay? So once we get the final activities after 10 years and also the decay constant, then we can determine the numbers of nuclei after 10 years. So we will take the activities 8.44 to the power of 9 divide by the decay constant 1.78 to the power of -9. So I'll get the numbers of nuclei after 10 years will be around 4.74 to the power of 18 nuclides. Okay, now we solve the question.